Hi everyone, my name is Pierrick Malecot, and today I will present a work done in our Applied Mechanics department of the FEMU Research Institute in France. This work is mainly the one of a former PhD student, Dr. Gomala Habsari. It was realized with two of my colleagues, Professor Sébastien Thibault and Dr. Fabrice Richard. This work title is Identification of Inelastic Cyclic Behavior of Thin Metal Sheets under Very Large Strain from Instrumented Microforming Process. So this work was funded by the Banque pour l'Investissement in France. So it's the bank for investment in France. So maybe a few words about the place I work in. So the school, it's called NSEM. So it's a National High School for Mechanics and Microtechnologies. The school was founded in 1902. It's a French engineering school, what we call Grandes Écoles. And this year we have around 900 and 1,000 students. So it's not a lot for university, but for an engineering school in France, it's quite big. So if you need more information about the school, just check on the website. So the research institute is called FEMU Institute. It was founded in 2004 by the fusion of 5 laboratories. It's a mixed research unit between the National Center for Research, the Engineering School NSEM, the University of Bourgogne-Franche-Comté, and the University of Technology in Belfort-Montbéliard. Around 800 people actually work in the FEMU Institute. So I'm a doctoral engineer in engineering. I'm an associate professor in NSEM and the Applied Mechanics department of the FEMU Institute. I'm the head of the manufacturing process and metrology teaching group. And I'm also a program manager for international relations in NSEM. So if you need any information, don't hesitate to contact me on my email address. As you see, I'm also a member of the French working group and standardization for topography and roughness analysis, and section manager for a micro manufacturing research platform called Mephisto for the metrology part. Maybe you don't know, but Besançon, it's here, very close from the Swiss and German border. So I will present this work in 5 parts. So the first part will be the context of the study. Next, I will talk about the identification procedure for thin sheet material behavior with new methodology, micro in-depth test. I will then talk about some tests to validate the plastic damage behavior previously identified by micro in-depth test. Then I will show the capability of micro in-depth test to predict the forming limit curve of thin sheets. And finally, we will see some conclusions and perspectives for this work. So this work is the fruit of a research project between 2 laboratories and 6 companies with nearly 4 million euros budget. So the main goal of this project was to develop new type of connector, which is cost effective and has a high performance. So we work on the material characterization aspect, and the other laboratory, the GRESPI, works on simulation and process to simulate all the processes used during the microconnector manufacturing, as cutting, bending, forming, welding, etc. So as I said before, our work is to supply the suitable material parameters to GRESPI, and this parameter will be used to realize processes simulation. So we use some experimental tests to identify the material parameters. Within this work, in regards to the material, we have some limitation. So we are working only with copper alloy strips, and so the thickness of these strips is 0.13 millimeters, and they are 15 millimeters width. They will go under a very large strain, and we are having the phenomenon of out-of-plane solicitations. So as a quick recap of our mission, we have to identify the constitutive law of thin sheet metal adapted for the process simulation. So to accomplish our mission, we must face the challenges of establishing the characterization method for mechanical behavior and for formability of thin sheet metal. So everybody knows that there are already several methods to characterize the material. So why do we need to develop a new one? So that's the object of the following slides. So the most known experimental test is tensile test. Tensile test have two main weaknesses for the work we are trying to do. First weakness is that tensile test goes under homogeneous and plane deformation, and maximum strain for copper alloy, it's rarely above 50%. So this doesn't match the requirements we have for our characterization, which is out of plane and maximum strain above 100%. We also used some bulging tests, but as our strips are very small, we need to develop a new setup for this experiment, and the size is very small. So the sealing will be very hard to obtain to answer the pressure, and in copper alloys, the maximum strain is just around 70%. But as you can see here, with the bulging test, we can undergo one of our requirement, which is out of plane test. We can also make some shear test. So the specimen geometry is very simple and very easy to obtain. But Once again, the deformation type is plane, so it's not what we are looking for, and the maximum strain we can obtain, it's around 30%, so it's not enough. So we developed a new type of characterization test. The name of this new characterization test, it's micro-indef, for micro-incremental deformation test. So this test has a lot of advantage. So the geometry of the specimen is very simple. We can go under an heterogeneous and out-of-plane deformation type, and the accumulated strain is above 250%, which is very high. So this test match with the requirement of the project. We can go under out-of-plane test. We can go above to 100% deformation. So it's and as the specimen geometry are simple, it's easy to manufacture them in a very small strip. We also developed another test because, as you can see in the previous one, it has one weakness. It's very simple with digital image correlation. So we try to think about another kind of test which permits to use digital image correlation. So we go with what we call TIX. This test will be explained later in the presentation, but this test match all the requirements. So this table sums up all the qualities of the different experimental tests. Therefore, we can see clearly that micro-indef test and TIX test are capable to answer our needs. So I will firstly present micro-indef test as the characterization test, and later we will talk about TIX test as a validation test and as a potential candidate for material characterization methods. As I have shown in the previous slide, classical characterization methods didn't fit all the requirements we have for this project, but micro-indef test did fit all of them. So we propose to use micro-indef test as a characterization method. Micro-indef test is inspired from micro-incremental sheet forming. The first part of this presentation will explain the identification method, and will show that the results we obtain with this method are reliable. Micro-indef test is performed on a micro-milling machine, like this one we have in the laboratory. During the test, the forming forces are measured with a dynamometer that lies below the forming device, and the forming forces are recorded by a computer. The forming device itself consists of a die support, a modular die, and a blank holder. The sheet metal here is placed between the blank holder and the modular die. So to ensure the immobility of the blank during the forming, 4 screws are used to fix the blank holder. The micro milling machine we use is very accurate. It's a Kern Evo, and the repeatability of the machine is 1 micrometer, and the precision of positioning is 0.1 micrometer. So the geometry we use for the characterization test in this project is a tiny pyramid, as you can see here. So the geometry we use for this project corresponds to the width of the strip. So the pyramid has an area of 3 mm by 3 mm with 2 mm height. The forming tool has 1 mm diameter. The lubrication with oil is sprayed directly on the blank on the tool during the forming. And we used several trajectory. So the forming strategy chosen here is constant Z level here, meaning that within one forming cycle, the tool forms a blank at a certain height until it returns to the starting point, and after that it goes one step under and follow the path for the next level, and so on until the end of the trajectory. So one forming cycle lasts around 30 seconds. So the material model chosen for this project is an elastic plastic damage coupling of Lemaitre, which consists of 9 parameters, as we can see in this table. 2 parameters for the elastic behavior, 3 parameters for the plastic behavior, 3 for the damage behavior, and 1 for fracture. So these parameters will be identified by using the micro-in-depth test. As you can see in the flowchart in the right part of the screen, just here, there are three parts to this identification. One is experimental test in blue here. One is numerical simulation, just here in red. And the last one is a minimization step using a homemade toolbox based on Levenberg-Marquardt algorithm. So we use a finite element model updating method in order to obtain the material parameters from the micro-in-depth test. The model in the numerical simulation here is prepared with MATLAB, meshed with and after that we reused MATLAB to generate the corresponding LSDyna keyword file. The identification is done in 2 steps. The first step used a tensile test, and the second step used a micro-in-depth test. So the idea is quite simple, on the paper at least. We have on one side an experimental test, the micro-in-depth test. We have on the other side a numerical simulation of this test using the elastoplastic damage coupling Lemaitre type model. And we use a minimization toolbox in order to minimize the difference between the experimental forming force and the numerical forming force. When this difference is minimized, theoretically we obtain the material parameters. The first step in the identification procedure is the initialization step. So from the experimental tensile test, we obtain the elastic and plastic parameters. So it's here. Next, this parameter will be used as the initial input for a tensile test simulation. So with a homemade toolbox for optimization called MIC2M, the value of each parameter is modified to achieve the one with the least difference to those of experimental tests. So when we arrive to this, it means that we have the suitable set of parameters to be used in the second step, which is the identification step. From the identification by a tensile test, we now have the elastic and plastic parameters. However, we still need the damage and fracture parameters in order to start our identification. So these damage and fracture parameters are obtained from the literature. So with this set of parameters, we can perform our micro-in-depth simulation, and thus we obtain the numerical forming forces. As explained before, by performing a micro-in-depth experimental test, we obtain the experimental forces. As with the same manner as we did on the tensile test identification, we use our optimization toolbox to achieve the parameters value, which has the least difference between the simulation and the experimental ones. To make it simple, we have the forming forces from the numerical simulation. We have the forming forces from the experimental test. So we compare both, and using the optimization toolbox, we are looking for the least difference between the experimental and the simulation forces. When this is achieved, we have the final set of the material parameters value. The identification procedure computing time is quite big. We use a cluster computer with between 16 and 20 processors, and the whole calculation takes around 5 days. Within this research, we have identified various copper alloys such as beryllium copper and brass, and copper iron, often used in electronic industry. The first set of results presented here are for copper iron, which are obtained from identification with micro-in-depth methods. The graph on the right compares the results between experimental tests and the simulation obtained from micro-in-depth. This validation set is realized with an helical path to form the pyramid, so it's not the same trajectory as the one used for the identification. So the result is quite good. As you can see, the forming forces is very well predicted. We can note here that phi represents the number of grain in thickness. We will talk about it later. Now we have the identified parameters. The question is, do we have the good ones? Are we sure these parameters are not just some value from mathematical fitting? If they are, then our chosen method is not good to validate the constitutive model. Another question we can ask is, do we really need to use micro-in-depth test instead of just tensile test to obtain these parameters? The first step to answer these questions is to be sure that the forming forces, namely Fz, depend on the material parameters, which means with the modification of material parameters, the forming forces will also be modified. Therefore, we performed the sensitivity study on parameters from Le Maître model. The graphic shows that the micro-indef FZ is sensitive equivalently to all parameters. As you can see here, all the black graphs have the same height, while tensile force is sensitive to plastic and elastic parameters, but is not sensitive to damage and fracture parameter, at least not very sensitive. Moreover, the sensitivity of tensile force is lower for overall parameters. Knowing that axial force is sensitive to parameters is necessary, but it's not a sufficient condition for parameters identification. The information richness contained in the forming force should be quantified with an identifiability index. Identifiability determines if there is enough information from forming force to identify constitutive law. So this criterion is based on the work of Richard. If the criterion is lower than 2, it means the parameters can be identified. If it's higher than 3, then they are unidentifiable. If we check micro-indef test with the black graphic, we can see that with all parameters, the identifiability stays under 2. That ensures the identifiability with forming forces obtained from micro-indef test is the good choice. As you can see, it's possible to identify plastic parameters with tensile test. It's no longer possible to use tensile test to identify the damage parameter because the identifiability factor goes beyond 3. I don't have time and I don't want to develop some mathematical calculation here, but we can just note that identifiability index is based on the calculation of the Jacobian matrix. This study has also been realized on different grain size, which means that we use different phi ratio. And with micro-indef test, we obtain a set of parameters for each grain size. Evolution of some parameters on phi is represented with this image. For initial yield stress, we found a typical Hall-Page type law, which means that the elastic limit has a variation with the inverse square root of the grain diameter. At the beginning of this part, we had two questions. The first one was how to identify the mechanical behavior of thin copper alloy sheet metal, and the second one was, will we obtain a set of reliable results? The answer is that we can identify the mechanical behavior by using micro-indef test and FEMU method with a Lemaitre type law for thin sheet behavior. And moreover, we have shown that each value of Lemaitre material parameter has a physical sense. Now that we have identified our material parameters and developed a method to prove that they are not just a mathematical fitting, but that they have a physical sense, we want to use this parameter in other kind of simulation to prove that they can simulate other tests. So as we explained before, phi is the ratio between thickness and grain size. So phi represents the number of grain in the thickness. The first validation test we try with the parameters identified by a micro-indef. It's simply a tensile test, but on a different grain size. So the quasi-static tensile test is performed with an electromechanical MTS machine. The strain measurement is done by a laser extensometer and a digital image correlation. To ensure the repeatability, each time was repeated 3 times for the same grain size. So the experimental results show a dependence of the mechanical behavior to the grain size. The finite element simulations are realized by using the material parameters obtained from micro-in-depth tests for each grain size. The simulation results show the same influence of grain size as of the experimental results. By visual comparison to experimental graph, the result obtained from simulation is coherent. For example, here for phi 9.54, the difference between both graphs are less than 5%. The second validation test I can present here is what we call the TIX test. So TIX, it's in the family of punching tests, with the particularity of having a geometrical aperture in the blank, as you can see here in different examples. TIX, which is an abbreviation for Tooth-on Linux, is an out-of-plane mechanical test. It's originated from the PhD work of Thomas Potier. The modification done within this research is by downsizing approximately 6 times the original system to correspond to the geometry of our copper alloy strip. So the goal of choosing this test is to validate the material parameter obtained from micro-in-depth test, because the advantage of this test is that by modifying the aperture in the blank, we can obtain different solicitation fields, as illustrated in here with these 4 examples. So therefore, we can validate the identification by micro-in-depth test on different loading cases by only changing the specimen. The set of TIX device consists of a blank holder, die, a blank, and a punch. So the TIX test was simulated numerically by a finite element model using the material parameter obtained with the micro-in-depth method and for different grain size. For the experimental part, with the downsizing of TIX setup, we are facing some difficulties. First, the alignment is hard to obtain. The alignment between the punch and the experimental setup, considering that the punch is fixed to the crosshead of a tensile test machine, and the setup is fixed on the mobile part of the tensile machine. The alignment between both is not good enough, especially with very small blank. I forgot to say that the diameter of the blank here, it's 15 millimeters maximum, because the strip is 15 millimeters. Furthermore, with the small size of our blank, we need to greatly magnify in order to observe the strain evolution clearly. So this generates different problems, a very limited depth of focus, and a requirement of having the camera completely immobile to avoid capturing blurry images. And we have exactly the same problem of focus depth and blurry image when we have to calibrate the IC system. So after some tryouts, we have designed and manufactured the system as you can see it here. This system resolves all the difficulties we have encountered. For example, for the alignment between the punch here in yellow and the blank, the punch is no longer fixed to the tensile test crosshead, but to a column system with a counter spring. For lighting optimization, LED spotlights are adjustable independently to the camera. The camera are fixed on the lower part of the setup here. And to resolve the last problem, which are the focus depth and blurry image, we use new lenses and we optimize the distance between the camera and the specimen. The last point is to ensure the calibration. So to ensure the calibration, we use 15 by 15 targets with black light. So this target is positioned within a calibration system, which enable to keep the target center immobile while having the degree of freedom necessary to make the calibration of the DIC system. So these images show the final testing system. The specimen is here. The specimen is produced by wire electric discharge machining, and the speckles are applied to be used by a stereo correlation system. To measure the punching force, we have to take into account the spring force. So the reference test is illustrated in the graphic. We first made a test without a specimen to measure the counter spring force, and then we conducted a normal test with specimen in the system. So in this slide, we can see some results from TIX test for brass with the help of the system we designed. So we are capable of measuring the Z displacement and the out of plane deformation, for example, the major strain. We can see with this image that it's possible to observe the critical zone. The comparison between experimental result and the simulation shows that the identification with a micro-indef is good, even to simulate some very complicated tests as this one. The question asked at the beginning of this part was, by using the material parameters identified with a micro-indef, can we predict other tests? The answer here is yes. We have shown that with this parameter, we can predict tensile test and TIX test. And I can add that we have a lot of other validation tests that I don't present here. So the last part of this presentation is the prediction of forming limit curve with identified parameters. Within the industrial framework, the concept of formability is necessary to define if a part is manufacturable or not. In microscale, the forming limit curves are used to serve this purpose. But the question is, will this approach applicable for microscale? And can we obtain a reliable experimental FLC? The second question is, by using the parameters obtained with micro-indef tests, can we have a numerical prediction of the forming limit curve? ISO 12004 takes care of determination of forming limit curves for metallic material sheets and stripes, to be precise. It also recognizes two experimental methods to obtain the FLC. There are Marciniak and the Nakazima method. The standard covers the rule for geometry of testing device and for the strip thickness. Unfortunately, the rules doesn't cover very well our sheet, because the standard specimen thickness has to be between 0.3 to 4 millimeters, and the punch diameter are from 75 to 125 millimeter, and our copper alloy strip thickness is between 0.30 millimeter to 0.21, with a width of 15 millimeters or 30 millimeters maximum. When miniaturizing the standard test into our scale, we were facing some difficulties with the test proposed. For example, the importance of friction is greater in microscale, especially for Nakazima tests. And to perform a Marciniak test experimentally, the difficulty is to achieve the blank sub-thickness size that correspond to our strip thickness. That's why we choose to, for simulation, to use Marciniak test, because we don't have the problem of manufacturing the sheet. But for experimental test, we use Nakazima. So the idea here is to use the material parameters obtained by micro-indef test as a way to achieve the forming limit curve numerically. So as I explained before, the choice of method for simulation doesn't fall into Nakazima because of the importance of friction in comparison to Marciniak. For this simulation, we use 7 different geometries. To ensure the deformation localization, a thickness of 0.1 mm is placed on the center of the specimen in order to have a non-uniform thickness. These simulations are performed for different grain size using the material parameter identified by micro-indef. The experimental Nakazima test is performed at Institut de Recherche du Puy-de-Dôme in Lorient under the supervision of Professor Pierrick. This test is performed on a thick roll sheet test machine, and the tests are performed on 8 different geometries to observe the deformation from uniaxial tension up to equibiaxial tension in order to obtain the complete FLC. To observe the deformation, we use the IC system and prepare the specimen with the advised speckle pattern. To minimize the friction between the punch and the sheet, we use a Teflon strip on the other side of the specimen, while on the punch we apply a generous amount of oil. The photos on the left of the page show the fracture of different geometries. We can observe on some specimen that the fracture doesn't take place in the middle. On the right, we have the forming limit curve we obtain with experimental work. We can note that the lower the phi, so the lower the number of grain in the thickness, the higher the formability. In order to obtain this forming limit curve, we were obliged to follow step by step the ISO 12004, and we developed our own algorithm under MATLAB. Because due to the size of our sheet, we cannot use the automatic forming limit curve algorithm in the Aramis software. So on the left side is the result of simulation by using Marciniak method with a friction coefficient of 0.05. It shows the same tendency that the experimental one. The lower the phi, the higher the formability. On the right side, we can see the comparison of result between the numerical simulation and experimental. At the first glance, it seems as if the simulation cannot predict correctly the experiments, because if you compare the yellow curve and the black curve, they are far apart. That's why we try another simulation with a higher friction coefficient, 0.1, and at that time you can see that the experimental curve and the simulation curve are really in a good agreement. This result shows that we probably had some difficulty with friction during our experimental tests. This problem is well underlined by the fact that some specimen didn't break in the middle. It's often a sign of high friction. So at the micro scale, we have proven that with material parameters obtained from micro-indef, it's probably more reliable to realize the FLC by numerical simulation than by experimental test, due to the great influence of friction during the experimental test. The question was, by using the material parameters identified with micro-indef, can we predict the FLC? To make it short, yeah. The numerical and experimental results show that we can predict with a very good precision the forming limit curve for the copper alloys. So let's now finish with some conclusion and perspectives. So this work demonstrates that micro-indef test identification to identify Lemaitre model parameters is not just a mathematical fitting, and that micro-indef test identification is more suitable than other tests for these materials. By using the material parameters identified with micro-indef, we predict the forming limit curve with a better reliability due to a better friction control. And the numerical and experimental results show that with less number of grain on the thickness, we have a greater formability. So micro-indef test was used by our colleague from another laboratory to make some simulation process for male macro connector and female macro connector, as shown by this picture. And the perspectives are numerous for this work. For example, we will try to use the TIX test as an identification test and not as a validation test. And we currently have a PhD student working on the improvement for the micro-in-depth test toolpath. We want to minimize the toolpath, for example, with some NURBS curve in order to reduce the computation time. We are currently working on the realization of an Indonesian traditional mask at a sub-millimetric scale. So the part is produced with incremental sheet forming, and a simulation of the process is realized by a finite element using the material parameters calculated by a micro-in-depth. This part was measured using a micro-nano tomograph, and the result compared with finite element result is very good, as we can see on this movie. So the difference between both is nearly zero, except for the nose and the bird here in pink, because the tool is too big to produce this thin part when the mask is very small. So terima kasih, and if you have any question, don't hesitate to contact me by email. Thank you.